Okay, according to my watch, it's about time to start. Everybody hear me out there? Anybody hear me? Hello?
Yes,
Yeah.
Okay.
Yes.
All right. Let's see. Short announcement. Maybe some of you already know this. It was in the planning and it was mentioned, but officially I got it there this morning. So there is a quiz for you to be looking at, which will be, according to Canvas, is set up to be due on Tuesday of next week. Not a very long quiz, I don't think, but should exercise your skills a little bit on the subject in preparation for exams. Okay. If you have the opportunity of, you can turn in on Tuesday, means if you did have a question on the interpretation of the problem, the way it's worded or something, you can always bring it up on Monday. And although I will not be able to tell you how to do it, if it is an interpretation of what the problem is asking for, it can help. And of course, I got 15 minutes at the end of the hour, so if you need that time, you can use that. Okay, unless there's some other questions, I'm going to go ahead and jump in and pick up where we left off. Okay, all right. As a short review, I'm going to use our table primarily to do that. I just refresh your memory that in this chapter, the focus actually is on 3 different Fourier series types, and that it would include the basic, which we started with, and then with the compact, and lastly, we were working on what's called the exponential Fourier series. And as far as the table goes, most of these we've already specifically talked about, you know, the recipes involved for the computation and where they came from. So unless there are some questions from last time, I think we're just going to pick up where we left off, which according to my notes was page 10. Any questions from last time? Okay. On page 10, we were specifically looking at an issue that is relevant to the computation for these coefficients. And that is, are there some tricks which would allow us to immediately determine if the coefficients are all 0? Okay, so this is it comes in that category. And the ideas, it seemed like at the time it was brought up, maybe wasn't yet clear, but the idea is based on something from, I believe it was chapter 2 that we talked about. I'll let you go back to that chapter in the notes and find it. If we talked about odd and even functions, you may remember that an odd times an even function is an odd function. That's helpful here. And if you integrate an odd function over a symmetric interval, you get 0. Okay, now I'm not reproving those because we discussed them when we covered the notes before. Trusting you may remember that. And if you have a question about it, it's a good time. This will be a good time to bring it up. And if you don't have a question about it, we're going to see why that is relevant to the Fourier series concern on computational coefficients. So for example, if what's listed here would correspond to the coefficients, the basic coefficients for the cosine, the sine, and the average value. And the question here was raised, well, if we if we realize and recognize that all the cosine functions are even functions, all the sine functions, the n omega naught t, are odd functions. And you can try this for yourself if you're not confident on it, but I believe you can see that's true. Replace t with a minus t, and then we know that the cosine, basically just the cosine of a minus x is the cosine of x, and the sine of a minus x is minus the sine of x. So that changing the t to a minus t here just identifies it as accordingly even and odd functions. So we know that the cosine function here is in fact an even function. Now the question is, well, what would be the correct symmetry for x of t that would guarantee that that coefficient would be 0?
If it was odd.
Odd, correct. That would be odd. Why? Because an odd times an even function is
another odd function.
Another odd function, right? And integrated. Now this is the part that we're a point that I want to clarify, and you're absolutely right. So the idea is our general recipe for the, let's take the AN as an example. Our general recipe just shows a T naught at the bottom, and that the interpretation that we've been using for that specific type notation is, well, we would get the same result regardless of the specific starting point and ending point, as long as the interval involved was T naught. Okay, and we knew that was the intent of that notation. So that being said, since it's arbitrary starting and ending, you could say, well, then we can always take a specific starting point and ending point for that integration. As long as the span is T naught, we're safe in doing that, and we know that we haven't changed the final result. So let's say, for example, we took a minus T naught over 2 to T naught over 2. We quickly recognize that is a symmetric interval. We're integrating over a symmetric interval, and when you get that condition of a symmetric interval, that's when you get 0. So the idea now is, well, and I think you told me the answer. If x of t is odd, then this works to give us 0. The important thing to remember here that may slip under the radar, so to speak, is that doesn't change the fact that the AN is going to be 0 back here, regardless of what the span of starting point, ending point is for the T naught. Okay, so it didn't require it back here, and we know these are equal. So the trick we did here was we took a specific case for that window to take on, which we know it really wasn't required, but we take it on anyway. And to illustrate that what's going to happen if x of t is odd. But we should have the confidence, okay, that this result didn't require us, it did not require us to actually have specifically those limits to be true. It was also true back here with the arbitrary inputs. You cannot change the left-hand side to be different than the right-hand side, is my point. Okay, a little bit of a subtle point is that it did not actually, in the end, it does not require us to have those symmetric limits to make that claim. Anybody out there get that idea? Or anybody have a question about it?
So you said cosine was an even function?
Correct.
So over a period, does it act like an odd function, or is it still even?
Over what?
Like, 0 to 2 pi, it cancels out. So does it act like an odd function, or is it still even?
Well, the cosine function will always, regardless of the n and the omega naught, when you set t equals 0, it'd have a maximum value, and then the how fast it changes depends on the n and the n and the omega naught. So I'm not quite sure how the answer to your question, but it stays an even function. And
Okay.
I think in brief that's kind of what I'm saying, but I'm not sure that got to the heart of it or not. Your question. So even as we change the n and the omega naught, that remains an even function. So we can play the same game. So then we can argue that well, if we take a look at the BNs, which are the coefficients for the sine, remember up here at the top, the BNs, we could argue, well, what would be if we wrote out the specific case where we selected a symmetric interval, which the claim is that you're going to get the same result whether that interval is symmetric or not. But if we did take that specific case for a symmetric interval, what would you claim the symmetry of x of t should be here to guarantee a 0?
Even.
Even, correct. So that would be then even symmetry. Because we know that even times odd is odd, and then integrated over a symmetric interval should give us 0. And yet we still remind ourselves that in order that result that it's 0 when x of t is even can be actually applied back here as well, where we didn't have symmetric interval. But the result has to be the same across that equal sign. All right. So the last one would be, if we take a look at, the last one would be for the A0. And looking at this, we see already we have a symmetric limit selected here as a special case of this one. So what would I write in here, even or odd for the A0? If I want the A0 to be 0, even or odd here?
Odd.
Correct. Okay. All right. So I think the point of this short and sweet discussion was that there are cases where we can use our knowledge of the symmetry of x of t to just completely eliminate part of the work we would have to do in the computation of the coefficients, because we can quickly recognize maybe the ANs or the BNs are 0 and cut the work in half. Any question on that? So that's kind of like the purpose of making this observation, is that it essentially can reduce the amount of work. Now, in principle, if you didn't take this into account, you still got to come to the same conclusion, of course, but this would allow us to essentially eliminate some of the work without actually getting into the nitty-gritty of the integration. All right, so let's see how this could be applied, and it is applied in this example 6.4. Now, in this example 6.4, we're given this square wave type function as we see it here. And the question specifically asks for the compact Fourier series, but we're going to go about obtaining the compact Fourier series using basically using our rules and coming up in the first stage with the basic Fourier series. So the process will be pretty much, going through the process of first coming up with the basic, and then from the basic going to the compact. And the convenience is, well, we've already got these rules in place for the Cn and the theta n that we need here. So all we then would need to do is get those, the ANs and the BNs, and we can get the CNs and the theta n's. for the compact. So our initial steps would focus more on the basic and as opposed to the compact, but then get to the compact via the basic. Okay, so to get the ball rolling here, along the top, we see formulas just repeated from the table for the BN coefficients, the AN coefficients, and the average value coefficient, DC. Now the question is, if we look at this function right here, to cut our work in half, I would claim what about that function? It is odd or it's even?
Even.
Even, correct. And because it's even, we could argue, then we look at the Fourier series, which of these coefficients, the BN, the AN, or the A's, should be 0? Can be automatically set to 0?
The BN?
The BN. I mean, you see why? Or anybody have a question why? Any questions on that? So all the BN coefficients will be 0.
Why? Why is it?
Well, that's because, in fact, to compute the BNs, we're essentially taking the product. We have to take the product of the sine function times the input signal, the x of t. Now we see that with the x of t has the even symmetry, and the sine function has the odd. Now remember, that means even times odd is odd. And we know we have the luxury, if we choose to represent that integration over t naught, span t naught, as a symmetric interval, minus t naught over 2 to t naught over 2. And therefore we would have, if you want to think about it, even times odd function being integrated over a symmetric interval, and therefore that's 0. That was a long answer, hopefully, to a short question. Did I get to answer your question?
Yes.
Okay. Now we'd be getting ahead of ourselves. We talk about the figure below, but that's the way it is in the, you know, in the figures that I can cut and paste. So we'll come back to that figure later. So we'll just, right now our focus would be to start off with that that computation for those basic trig Fourier coefficients. Ultimately, we'll get to the compact ones. Okay, so the idea is, well, what we just said was we don't need to worry about the BNs because the x of t is an even function. So that only leaves the A's, and when it comes to the A's, there's simply the average value of 1 and then the A sub n's. So we got to do those. Now let's back up for a moment. I'm sure I forgot to mention something important, as usual. In doing these calculations, it's usually, I mean, not that you have to do it, but sometimes it's helpful because it streamlines the calculation. And whether you do it now or do it later, I guess we're going to do it from the beginning, and we're going to make the observation that based on the particular figure we have here, we can see that we can see that in fact the period, okay, that's the interval of time over which it repeats itself, is in fact, let's do another one here, is in fact what? What's the interval, what's the span here for one period?
2 pi.
It's 2 pi, correct. And if you have a question on that, it's a good time to bring it up. So it's repeating with a time interval t naught, and we're going to say, well, from the figure, you can see that by inspection. And once you know the value for the period, you can always calculate the fundamental using that general formula. And since t naught is 2 pi, that's where you get the 1. If you plug in the 2 pi. Okay, we'll use that in a minute here. Okay, so here's the formula for the AN, which we can write it with, for our purposes, it may be easier to write it and compute it with a symmetric interval. Not that we have to, but I would say, let me claim why I would argue that it would be easier. Because if you do it over a symmetric interval, you're going to be doing it from minus pi to pi. Okay, that part I think you get. If we did it instead from a non-symmetric, let's say from 0 to 2 pi, in principle, there's nothing wrong with that. But in practice, then you got to represent the signal you're integrating in two pieces, the piece on the left and the piece on the right. So it kind of complicates the integration, and that really isn't necessary because we know the integration from minus pi to pi has to give us the same result as from 0 to 2 pi. So taking the easier of the two integrations to do, where you just have the x of t defined pretty much over one interval there, you don't have to break it up. You just, from minus pi over 2 to pi over 2, it's going to be 1 and 0 otherwise. So that would be the easiest choice. I'm not saying it's the only one, but certainly I think it would be the easier choice to make for the integration. So right here, we have to make a choice. All I'm saying is, and so I think if you look at the figure and think about it, this is probably going to be the best choice. All right. Now what we can do is, since I've got the T naught over 2 and the T naught, obviously we know that T naught is 2 pi, so this becomes pi and a minus pi. And the T naught is 2 pi. So we plugged in, going to the next step, we plugged in the 2 pi's wherever there was a T naught. Ultimately, we're going to change the omega naught too, but not on that line. So then one more step we can take, which you can see has to be correct. You see it has to be correct. If T naught is 2 pi, you go to here. But if we take into account the specific x of t, right? If we take that into account, we see the way that the x of t is defined, would have to be defined within that window from minus pi to pi, would suggest that we do not need to integrate all the way out to pi, nor should we. We can get rid of the x of t in the expression, just replace it with 1. But when we do that, we need to remind ourselves that that only would be 1 between a minus pi over 2 and pi over 2. And it's 0 otherwise. So you can drop the x of t. Okay, you can leave it there, but no reason to leave it there because x of t is 1 in that particular, with those particular limits. Now, where you want to put it, you want to switch over from omega naught specific to, which in our case happens to be 1, as we said, or just leave it as a symbol and then do it later. It's up to you, but I don't see any tremendous disadvantage to getting it plugged in early, so we're going to do it right now. So we notice that if the omega naught is 1, then the n omega naught t just simply becomes n times t, where n is an index. Any questions? Now we know we want to write this in the form of cosine u du. So it turns out you can say, if you want to do it in one step, this looks like an integrating factor by throwing a factor of n over n in there. And putting the n next to the dt gives it in the form of du, and then this becomes cosine u du. Now there's a little more details here. You can check it out. But it comes down to the cosine u du with that integrating factor with a 1 over n. So then you get the derivative sign is a cosine, so the integral of the cosine is sort of just simply going backwards the other way, so it becomes a sine, becomes the sine of u. But since we know that u is equal to nt, we can put in the sine of nt. Again, I don't like micromanaging you on your calculus, so if you think about it differently, but you get the same result, I'm sure it's okay. So then the idea would be if we did this integration, which we have to do, then we can replace that integral part with a sine of nt with a 1 over n in front. I got the pi's in here, but there they are. That pi goes there. And we see once I've gone back to the original limits with the t instead of the u, I can feel comfortable putting in the limits for the original t, which was integration with pi over 2 and minus pi over 2, which appears there. And I went through that fast, but again, I think this is kind of a calculus, but if you have a question, bring it up. So if we plug in for the t, right? So we're going to get the first just by substitution. That's how we get the first term, and minus by substitution the second term. And if we use the fact that the sine is an odd function, then the sine of a minus x is minus sine of x, and therefore you can pull the minus out. And notice once you do that, you get minus times minus is plus. So both of these being identical, that means it's a factor of 2. Okay, so what happens to this expression if n is an integer? Anybody out there hear the question? What happens to this expression if n is an integer?
It'll just be 1.
Oh, sorry, n is an integer. I mean, n is an even integer. I'll rephrase the question. Let's say n is an even integer.
Then it turns into 0.
That'd be 0, right? Let's try a few. Okay, n equal to 2. That would be a sine of pi. N is equal to 4. That would be sine of 2 pi. N is equal to 6. That would be 3 pi, etc. So yes, if n is an even integer, we can see from this, if n is an even integer, then that would guarantee our an is equal to 0. Now, before I leave the page, let me. I think I jumped over a line that I wanted to cover. Let's see. I don't remember talking about the computation for the average value. So we can. We see that the T naught is 2 pi. We saw that before. Again, we can replace the basically put in the T naught 2 pi. Therefore, you get a pi over a pi. But then basically, because it gets cut down a half again, because it's pi over 2. So if we integrate from minus pi over 2 to pi over 2, the substitution for T naught equal to 2 pi went in there. So when you do that, you get pi over 2 pi, which is 1/2. Now here's a little trick when it comes to calculating the average value, which you may want to keep in mind. Anytime you can make a quick check on your answer, visually it's usually helpful. And in this case, you can. Okay, and the idea is we may not want to forget, I don't even want you to forget, that the interpretation for the A0 is the average value of the function. So I would claim if all I did was show you that function, okay, x of t, what would your guess the average has to be? Calculations notwithstanding. What does the average of this function look like? What do you think about? What value would you get if you did the average of that function?
1/2.
1/2. Is that a guess or answer?
Answer.
That's right. That's the right answer. It's 1/2. Now, how do you see that?
Because it has an area of 1 and then an area of 0 over and over.
area of 1.
Oh, actually, never mind.
Well, I mean,
It has an
you're
area.
not necessarily wrong. I mean, let's say, for example, you took that area that you would get there, right? And you said, well, the area would be 1 times pi. But then you're integrating from minus pi to pi, and therefore, if you divide by 2 pi, you get 1/2. So, I mean, your area argument is not a bad one. I would just say that it's the area of this thing is not 1, but it's actually pi. And then you have to divide by the interval over which you did the average, which in this case is 2 pi. But I think we're both in agreement the average is 1/2. Now, another way to view this is you could say, well, half the time it's at 1, and the other half of the time it's at 0. Well, that's even an easier argument because we know then that the average of 1 and 0 is 1/2. All right, we kind of, maybe we beat that to death. I don't know. Any questions on that? So the claim is I mean, this was a little more quantitative than I had in mind. The simple argument I had in mind was the 1 and the 0 argument. But either way, as long as you can see it easily, that from the figure it does look like the average is 1/2, then that's always a good check. I mean, for example, if you got a number like 5 or 6 here, or a -1, your alarms should go off that maybe you made a mistake in your calculations. Okay. All right. So I'm going to go to the next page. We're not quite done with this page yet, or the next page yet. They're done with this page. We want to get to the next page. All right. So now what we were able to accomplish was to show that this is the AN expression. And for an even integer, which I think we demonstrated, the AN would be equal to 0. And we did demonstrate that on the previous page. Now, since we've eliminated all the even integers for the ANs, let's take a look at the odd integers. Okay, so to do that, I'm going to just look at the part which controls the sign. Okay, so we'd argue that just the sign part here. So if we take n equal to 1, that's the sign of pi over 2. And I'll let you check if you do the sign of pi over 2, that's 1. If we take n equal to 3, that would be 3 pi over 2, and that would be a -1. And n equal to 5, that would be 5 pi over 2, and that would be +1. I guess I have some notes here. We can see that basically that would be 3 pi over 2 would be the sine of pi. Or okay, 3 pi over 2 would be like the sine of pi plus pi over 2. Okay, and then this one be with n equal to 5 would be sine of 4 pi over 2 plus pi over 2, which we know is 2 pi plus pi over 2 is, and that would be +1. You already went around 360 degrees plus pi over 2. So we see that in fact, when we have odd integers, you can check this with your calculator, that we did the sine of the angle associated with the odd integers, it alternates between +1, -1, +1, etc. Now, it's a little awkward to just leave it that way. So some brilliant soul out there somewhere along the way figured out that there's a convenient recipe that you can substitute in for the sign here that will do exactly what the pattern we're seeing. And it's not my intent to derive this from first principles, but just to make the observation, yes, it works. And then once you see it works, then most of us being engineers are happy to use it. So the idea would be that that recipe looks like a -1, and the exponent would be n minus 1 over 2. Now, let's test that to see that it does work. So I would argue if we take our n's here, if we put n equal to 1, then that's going to be 0. So a -1 to the 0 is 1. If we put n equal to 3, that would be 3 minus 1 is 2. 2 over 2 is 1. A -1 to the 1 power is a -1. And if we put n equal to 5, 5 minus 1 is, what is 5 minus 1 out there? Anyone following me?
4.
4. 4 over 2 is 2. And a -1 squared is simply 1. So the contention is, and I'll let you check the next one in the list, which would be that we'd be potentially interested in, check it for 7. What's your guess? If you take n equal to 7, it has to be what has to result if we have n equals 7? If you look at the pattern.
-1.
-1, correct. And I'll let you check that this recipe does work for that. Okay, so we can then put in place of the sign n pi over 2, we can put in this handy recipe, which takes care of the dependence on n. I mean, we may want to remind ourselves we can only use this recipe for n odd. Okay, we've already established that for n even, all the ANs are 0. All right. So let's go ahead and list out the coefficients for the basic trig. And we'll use our handy recipe in doing it. So here's our rule right here. So for n equal to 1, it just simply becomes 2 over pi. And then again, -1 to the n minus 1 minus 1, we know that that's 0 over 2 is 0, -1 to the 0 is 1. So it's positive, A1 is positive, and it's 2 over pi. Now, this is the right time to speak up if this calculation wasn't clear for anyone out there. Because I think once you see that first one, the other ones will kind of fall into place pretty fast. So we're only interested in the odd n because we already know what happens with the even n. According to the even n, all the ANs are 0. So for the odd n, the next odd n would be 3. That's the next odd number after 1. So we'll put in for n 3. So we get that amplitude of the A3. But then we see, in fact, we got to include that recipe part, and for 3 minus 1 is 2, 2 over 2 is 1, that's a -1 to the 1 power, which is a -1, so it's negative. And negative 2 over 3 pi. And we go on to the 5, we can see, and we did check this already, then you'd expect that they put for n equal to 5, you guess where the 5 comes from. We already checked that part, we know that's positive. And for the 7, it comes out negative, as we talked about before. So here's the listing for the first coefficients. You could say that we've actually got them for the even ones numbers too, even n, because we already know they're 0. And we've also got the A0. All right, any questions? So we can write out, you know, our first, you could say, well, here is an intermediate step for the Fourier series. We've already taken into account the fact that we know the A0 is 1/2. We've already taken into account that since the x of t is even, all the b n coefficients are 0, therefore there's no signs. And we've already taken into account that we know all the AN are zeros for n even, therefore the only n that we need are the odd n. So we can be a little more specific. We can now plug in our expression for the a sub n, which should be up here. And we plug in our expression for the a sub n. Now, in doing that, what happened here? What factor seems to be common in all these terms? Anybody recognize that factor that seems to be common? What factor do all these seem to have in common?
2 pi.
What?
2 over what? Pi. 2 over pi is common to every one of these, so we can factor that out. Now, all you then need to do then would be to look up here at the top and start to plug in, and you see if you just write it out, here's your Fourier series, basic. That would be the trig basic series, and yeah, we can see the pattern here. Let's see if we can figure out the pattern. If I was going to write out what the next term would have to be, notice it goes plus, minus, plus, minus. So what's the sign of the next term?
Plus.
Plus. What do I divide by? Here I was dividing by 7. What do I divide by in the next term?
9.
9. And then, and is it going to be a sine or a cosine? Which one should it be? Cosine, right? Because the pattern seems to be cosines. And so what do I write here? I have 7t. What should I write here?
90.
90. And I'll leave it to you to figure out the term after that. But we know it's associated again with an odd number. So that I guess instead of 9, the next one will have what? N equal to? What's the next
11.
term? 11, correct. So we can see the pattern. And so I would argue that if you were asked to just write out a few terms, this is great. If you said, well, for purposes of using a computer and maybe computing 100 terms to see how good the agreement is, which could hypothetically happen, then the summation recipe would be more helpful to you, because you don't have enough space on the page to write out 1,000 or 100 terms. But if you, with a computer, you can approximate that pretty well. Okay. Any questions? Well, so the first part was just simply to get the trig basic solution and use that as a bootstrap to the compact. So here we're going to connect the prior basic to construct the compact form. And I'm actually going back. You could say, well, the formulas I have written across here are the ones that are available off the table. So that table would be, it would be a valuable tool, let's say, potentially during an exam. So here our recipe for the CNs and the theta n's do appear there. Okay, and these were taken from the table, and yes, we did derive these. So, okay. So we can make some preliminary observations which are helpful for the construction of which of the CNs we need. First one is, because the A0 is not 0, we can immediately say we know the C0 because that's one of our recipes. So we don't have to, we just, if the A0 is 1/2, which it was, then the C0 is going to be 1/2. Now, what about the Cn? Well, with a Cn, we don't really have cosine. Let's put it this way. Everything's a cosine here, but we don't have the two cases where the ANs and the BNs, we just sort of as a consolidated effect. So, but so there's only one set of coefficients, Cn, period. However, we can use our understanding that we obtained from doing the basic to make an observation, which will help us in setting up the compact coefficients. And that is, the claim would be that the Cn are all going to be 0 for n, what, odd or even? Anybody out there get it?
Even?
And that's correct. Why? Now, in order to make that case, you have to argue two things. For it to be 0 for the even n, we would have to know the ANs are 0 for all the even n. Are they? What did we find out on the previous page?
Yeah.
Didn't we say B's of n were 0?
Yes, all the
Because it's an even.
ANs were, remember, all the ANs were 0 for the integer, for the even integer n. You follow me so far? Now, that's
Yeah.
not enough by itself, right? However, we had some other piece of information that would tell us that this is 0 for all the even n. What do we know about the BNs? Anybody? What do we find out about the BNs?
All 0.
All 0. And they're all 0 because what do we know about the x of t?
It was
It was even.
Even, right? And the BNs were the coefficients for the sines, which are odd functions. Did I manage to snow you on that one or not?
So the only ones that we were worried about is just the AN, because it's like the BN cancels out, so the AN squared just reduces to AN.
Yeah, but we're right now we're just making the point that we don't need to worry about all the CNs, only going to worry about the odd ones because we're making the case that the even ones are going to be 0.
Oh, okay.
Okay, so if that part is clear, then I think we're going to go. We can jump in and carry the ball the rest of the way here. So okay, yes. So the Cn are 0 for all even n, and yet we do know that we've got a DC term. Okay, so that'll be there. Now the only n's that are left, then we've taken care of the C0. And we know that the Cn is 0 for all even n, therefore what's only left are the Cn for the odd n is where we would need to go. Now, since this is kind of a bootstrap process where we're using our knowledge of having done the basic trig, we're going to say, well, from our work on the basic trig, we found out we had this recipe for the AN when the n was odd. So we can use that here to make the case. Now, but the case is not intended as a complicated one, but the only, let's put it that way, the only impact, there's two factors here. There's a 2 over n pi, and then there's this -1 raised to this exponent. Well, we saw before that the only thing that can happen here, you can either get a +1 or a -1. But then we asked the question, well, if you square the AN, will there be any impact? If
No.
it's no. No, you know, basically you're going to square the AN, then take the square root. So even if there was a -1 there, it gets squared, and then that gets lost. Okay, in terms of information. Now, not that lost completely. We'll see that the information's still there, but it's somewhere else. So, so the idea would be then, well, if this is our formula for the A sub n, we knew the B sub n were all 0, then, and for the n odd, then we can just go ahead and as well as for all of them, in even or odd, in the Bn case, then we can go ahead and square it, and then take the square root, and we're just going to get that 2 over n pi. With no information about the sign that was originally associated with the A sub n. Any questions? Okay, so so now we know the CNs also. And so where our focus is going to be is on the last step, since we got the C0, we got the CNs. We know what they are for all the even ones, and now we even know then what they are for the odd ones. The only thing left would be the theta ends. Now to get the theta ends, this really is not as bad as it looks. We have this formula up here at the top. Now, if we look at the formula, we see that inverse tangent rule that we came up with has the Bn in the numerator of that ratio. Now, what do we say all the Bn's have to be? Whether it's even or odd. They're all going to be 0, right? All 0. And for the cases of the n odd, we know that the ANs are not going to be 0. So 0 divided by something is always 0. Okay, so we basically got an inverse tangent of 0. Okay. Now, whether you use your calculator or whether you need a picture or prefer a picture, I don't say you need it, but let's say you prefer a picture, you may remember that in the second page of the notes for the Fourier, we've got the inverse tangent showing up, and we see that, in fact, when the inverse tangent is plotted versus x being the argument, we see that when the x is equal to 0, what's the inverse tangent? Can everybody see the figure? What should the inverse tangent be if I said x equal to 0? 0, right. Now, it's not that we use the inverse tangent every day, but if you wanted to check it with your calculator, I encourage you to do that. But point is, we can, if you use the standard graphical representation, it would look like that. And we see that that's 0 when x is 0, which tells us there's 2 parts to this contribution to this angle. There's the first part, which if you know, based on everything we said, that first term will always be, what am I thinking?
0.
No matter what n I pick, or you know, I'm always going to get that first term to be
0.
0, right. So the only place I'm going to get a non-zero angle theta n would be the second term. And according to the rule, that term would also be 0 if the AN is in fact positive. So we only do this plus or minus pi thing when AN is that was not a hypothetical question. What is it? So what is it? If AN is what?
Odd.
Oh, no, I'm thinking in terms of sign. When do you add the pi in? You add the
When
pi
A is
in
negative?
when the AN is
Negative.
negative, right. And we saw that happen, right? Didn't we not? We saw that happen when we were looking at the, let me find page 13 here. When we looked at the ANs, we saw that in fact, the ANs could be negative. Here it went plus, negative, then negative there. Then it was plus here, then negative there, right? So we saw the ANs do switch signs, and therefore we would expect that for the ANs, if the AN is negative, we need to add that pi in. So if we list our ANs, and I guess we're not listing all of them, only a few. If we list our ANs here, okay, that I think would be consistent. Notice when plus, minus, plus, and we can imagine the A7 is going to be negative. We know all the BNs are all 0 no matter what, including the even ones, but we don't need to itemize those. And then the CNs go according to the rule we had here, okay, which are listed here. And then the theta ends, because the first term is 0, the only time we need to add in a pi or minus pi is when the AN is negative, but that first A associated with A1 is positive, therefore no pi is added in. For the case for the n equal to 3, again an odd number, we see it's negative, therefore we can elect to either add a pi or subtract a pi. It shouldn't matter in principle. And go to the 5 case, the n equal to 5, again we see that's positive. Because it's positive, we don't have to add in a pi, and it's 0. Any question on that? Okay, I think I'm bordering on being out of time. I did promise you to be available for questions if you got it. If you let me know now, I'll stick around. If you don't have questions, then I'm packing up and heading home. Any questions? And if we're pretty much done, I could probably, I think we're done.
I'd had one question for you.
Okay.
On the homework 5 that you have posted for this class.
Let me see, homework 5. Homework 5 is the 4U series homework, right?
Yeah.
Okay, let me see if I got haven't got a chance to even think about, I don't know if we got far enough to open the floor to question. Let me see if I got my homework 5 here.
Oh, okay. We're not through homework 5 yet. But my question
We're getting
was
close, and we're not that far. I just didn't print out the problems, and I don't know if I posted a solution yet.
Okay.
I think I did post some problems, but I didn't post. Can you tell me a little bit about your question? Then I'll make sure I have an answer ready for you on Monday.
My question was about the answers to the problems.
Okay.
Like the key. I didn't know. I
plan to post the solutions over the weekend.
Okay. That was my only question.
Okay, no, that's a good question. I had in mind to do it, but I'm glad you reminded me. So yes, I will be posting the solutions to that homework very soon.
Okay, thank you.
Very soon. Any other questions?
Yeah, I was just gonna see if you could go through one of the problems from the homework 4 with me.
Homework 4. Oh, homework 4.
Right.
The problem, I have it's not that I don't want to help you, but let me ask you, my problem is we already opened the floor to questions on homework 4, didn't we?
Yeah, I thought this was your office hours after the.
Well, even on
class.
my office hours, I'm kind of limited how much help I can give a student once a quiz hits the ground running, so to speak. In other words, once I have a quiz out there, the idea being that, well, you know the question I'm asking, and it's probably one you should have realized might be asked. I mean, in a sense, we're kind of like in class situation as far as the quiz goes. As draconian as that sounds, I'm reluctant to reverse that philosophy. In other words, the idea being is once the quiz is out there, it's just like taking an in-class quiz, except for no one's sitting over your shoulder watching you.
Okay, I mean, I would have asked earlier, but I as far as your announcement goes, like today was the
But
first
let
day
me
your
ask you
office
this,
hours
what I
started.
can do as far as the quiz, if it's a question related to the quiz, I can try to tell, if you're confused by part of that question, I'm happy to address the issue. Well, you know, what is it asking for?
I don't know if it's a part of the quiz or not because I haven't done the quiz.
Oh, okay.
I haven't.
Yeah,
looked at
well,
it.
see, that's fine.
But
I tell you what, we can get this answer, just like I said, I'm really kind of reluctant to cross that bridge where I'm answering questions after a quiz has hit the ground out there. Even though you may not have seen it, I can't be sure who has and who hasn't. So I would say that let's get your question answered after the quiz.
okay,
How about that?
okay,
Yeah, bring your question up right after the quiz, and then whatever it is, we'll make sure, because that's where the heavy artillery part of the course is in the exam, not in the quizzes. So let's get your question answered, but let's do it after the quiz key comes out.
okay.
If that's okay. That's kind of like how I'm doing it. All right, any other questions? All right, then, like I said, I think I'll pack up and I'm gonna head home.